Okay, welcome to the class, and now we know that we are discussing MIMO transmission. Okay, and this class is mostly about learning the idea behind why 5G transmits 2 transport blocks. Okay, even though the number of layer is 8. Okay, right? Why it transmits 1 transport block when the number of layer is up to 4. Okay, right? We'll try to understand this because these are basic questions which one needs an answer, that why it is the architecture is implemented in a peculiar way. Okay, right? So we will first try to understand what are the different possible options in theory. Let's say if there is number of layer is 8, how can in principle it be implemented? Why did standard not go about doing it in that particular way, okay, and why it is doing it in a way which we have just discussed, right? Okay, correct. So this is the idea, so that we have answers to all these questions. Okay, now what is happening? So this is, we have seen 5G MIMO transceiver chain, but this is a reference. Okay, and we understand this. Okay, this is what we are going to focus on. Okay, right? Why it is implemented like this. Okay, why there is only maximum of 2 transfer block, even though the number of layers can go up to 8. Okay, right? So just to give you an example, if the number of layer is 8, why not 8 different transfer blocks coming from here? It could come, right? Okay, then I mean that is also one option. Okay, we'll try to understand why it is not done like that. Okay, I'm jumping the gun and telling you that this is an option, but it is not implemented like that. Okay, so what is implemented? That it passes on, MAC layer passes on only 1 or 2 transfer blocks. Okay, and the related control information. Okay, so what is this? This is a summary. Okay, just to recapture whatever we have done in last 2 classes in one slide. Okay, and what happens? 5G MAC layer sends maximum of 2 transfer blocks in the downlink. Okay, and by the way, this is whatever we have discussed is applicable for downlink. Okay, in uplink is only 1 layer. Okay, if you look at the physical layer chain in the uplink, okay, standard allows to a transmission of only 1 transfer block. Okay, in the uplink. Okay, right. So what will 5G 5 layer does? It will process maximum of 2 transfer block to generate 2 modulated code words. Correct? Okay, we know that. Okay, we know that by heart now. Okay, and what is this? So the modulated symbols for these 2 different code words, if there are 2 different transfer blocks, okay, from q is equal to 0 and 1, are denoted like this, right? Okay, fine. And this is, what is this? MQ symbol, number of modulated symbols in qth code word. And how many such code words? 2 code words. Okay, corresponding to each of the transfer block. And 5G layer supports maximum of NL is equal to 8 MIMO layers in the downlink, and it is time to stress upon this fact. That's how DMRS are designed, right? Okay, the DMRS is maximum number of ports in DMRS is 8 because they are transmitted with data. If data is not exceeding 8 layers, why should DMRS be exceeding 8 layers? Right? Okay, this is what we are talking about, release 15. Okay, fine. So of course they are as I said earlier, they are closely, all these designs are closely coupled. DMRS design is closely coupled with this design. Fine. Okay, so layers are indexed from 0 to nu minus 1. Nu can be up to 8. Number of layers, there is a layer index. Nu is the layer index. Okay, right. Now why up to 8 layers? Look at this. Well, that's another question we need to have an answer, right? Why not 16 layers? Okay, correct. So it is practically difficult to have channel with rank greater than 8. Okay, in the kind of scenarios for which 5G system is designed, okay, the cellular system, then typically what people realize after doing extensive channel measurement campaigns, okay, actual channel measurement wherein you transmit the signal and then observe what kind of channel it is. Okay, and doing those kind of experiments in different scenarios, okay, what people observe that with a very high probability you can only observe channel ranks up to 8, okay, not more than that. channel 8 is also maximum. Okay, most of the time rank is between 2 to 3. Okay, but people, if you have a highly ideal scenario wherein base station and users are close, and then you have like user is not observing too much of interference, all that. Okay, right. In the what I am saying here is in a highly ideal scenario, you could see ranks up to 8. Okay, right, and that's why you see this is the architecture which standard supports. Okay, this is like physical layer architecture is like being supported up to 8 layers. Okay, and for layers up to 4 layers, 5G max will send single transfer block. That's what we understand. Okay, right, and physical layer will process this transfer block to yield a code word which is demultiplexed into new layers. Okay, fine. For the rank between 4 to 7, if the number of layers is between 4 to 7, Phi receives 2 transfer blocks which it processes to give 2 code words. Right. So for this case, MAC layer sends 2 transfer blocks in the downlink. Okay, this is a summary. Okay, now Phi will process this transfer block to yield 2 code words which are demultiplexed into depending on how many layers you have. Okay, it can be from 5 to 8. Right. Okay, correct. So that's how the processing gets done. Okay. Now after understanding this, okay, what the questions what we are trying to answer is like why this kind of architecture. Okay, and that's over next 20-25 minutes we'll try to answer these questions. Okay, first question we have answered over here, that why only 8 layers, why not more than that. Okay, so this is like you could say that in practice with very small probability I could the UE could observe, okay, channel rank greater than 8 also, but since that doesn't happen most of the time, it happens only with very small probability, why design a system for that? Right. Okay, that's over designing the system which nobody is going to implement also. Okay, right. So nobody might tell you, but most of the time people might be implementing only up to 4 layers because users might not even observe up to 8 layers. Okay, because you look at this, right, that you have to process 2 transfer blocks, your system should be designed for that also. Right, then standard gives you an option, but I might not support. My system, my base station might not support. Correct? Okay, because if you have to support till 8, you need to design your system, you need to invest that kind of money, you need to build a costly system. Right, so that's and if you build a costly system, operator might not even buy it. Right, so what will you do with that system? There have been these kind of technologies which were very nice, okay, which were giving at their time much higher data rate than the existing systems, but they were exorbitantly costly. Okay, so they failed. Okay, so system designers, operators, they are very careful. Okay, each penny counts. Okay, right. So that's how these systems are designed. Okay, so you have to keep all this in mind when you are designing a system. Okay, so this is one part of it, but the more theoretical part of it, what we are talking about here is as follows. Okay, let's say that we are talking about NL layers. Okay, so we are talking about this code word to layer mapping. Right. Okay, we looked at this mapping block. Okay, and what are we saying here? Okay, so I am looking at this multi code word transmission. Okay, what am I saying here? That if the number of layer is, let's say, 4, okay, why is standard or the MAC layer transmitting only 1 transfer block? Okay, why not NL different transfer blocks being transmitted? That's the question I am trying to answer. Okay, right. So if, let's say, just we assume it doesn't happen in standard. Okay, but what am I saying? Let's say if you want to design a system like that, wherein if there are NL layers, okay, so you get NL transfer blocks, right? MAC layer can give that. Okay, right. What happens in that case? So you will have NL different different physical layer transmit chains, wherein when CRC, which for each of this transfer block, you will have a different transmit chain. Correct? okay, and that's what we are saying. The standard refers to this LDPC coded and modulated transfer block as a code word, okay. So this modulated code word I am talking about, okay. So how is this modulated code word generated? You remember the physical layer chain, okay. So each of this transfer block undergoes processing, okay, and then one modulated code word is generated. Now if there are NL layers and then MAC layer is giving you NL different transfer blocks, right, you will have to do processing, you will have to do this processing for 8 different transfer blocks, correct, okay. We understand, right? Instead of, what did we do for NL is equal to 4? We took one transfer block and demultiplexed into 4 different layers. Now the way we are arguing here is that you get NL different transfer blocks, you do the processing for each one of them, right? CRC, segmentation, LDPC, right, rate matching, and that's what will be done for 8 different layers. That's what I am showing you here. This, when I write this coding modulation, coding modulation, coding modulation, what I mean is the complete physical layer chain for each of this layer, right, okay, and you take this, then there is not, you will not need this mapping block, correct, and what happens, you precode this and transmit over NT antennas, fine. You get what am I saying here, okay, that instead of taking one transfer block, demultiplexing them into 4 different layers, you don't have that now. You, from the beginning itself, you have 4 different layers, and you do this modulation coding and the complete physical layer chain for each one of them, then do the precoding and then transmit it over the antenna. That's also one architecture, right? But the standard has not implemented like that, but that's one architecture, okay, to transmit NL layers, fine. Is this idea clear, okay? So what is this kind of transmission is called multi-code word transmission, okay, right? Forget NL is equal to 8 layers, if there is only NL is equal to 4 layers, okay. One way, what we have done is only one code word. You get one transfer block, right, and the way it is implemented in the standard, one transfer block, you get one modulated code word. That's how it is done. What I am saying here is that there is another way of implementing the system, right. You get 4 different code words, okay, and this is called multi-code word transmission. Up to NL is equal to 4 in the standard, we are doing only single code word transmission. But there is, if you are to, you could implement it like this, wherein you transmit 4 different code words, fine, okay, and that chain, abstracted chain will look like this: CRC, segmentation, LDPC, right, interleaving modulation for each of this layer, right, okay, fine. So what will happen in that case? That's what I am telling. MAC layer will give NL transfer block to physical layer. We argued about it. Fine, okay. Physical layer will attach CRC to each of this transfer block and generate and perform separate coding and modulation on each of this transfer block, correct? That's what is going to happen, fine, okay. So this is one architecture. This is also possible, okay, right? And what are the, if before like coming up with the architecture which is there in the standard, people argued about this also. Why not implement MIMO like this, correct, okay? And what are the advantages and limitations of this architecture? Okay, that's what we are going to discuss, so that it becomes clear that why it is done in the present way, okay, correct. So if you have this kind of architecture, you do this processing at the transmitter, okay, and the receiver you have to do the reverse processing, okay, fine, and I'll show you the receiver for this kind of architecture, okay. Let's see that. So keep this in mind, keep this architecture in mind, okay. There are 4 different separately encoded NL layers, okay, right. Each one of them has undergone different modulation and coding, right, fine, okay, right. Now at the receiver what will happen? That's what I am going to show you, and then we will discuss and debate why this was not done, okay, right. So let's see that, okay. So this is, if you do the architecture, if you design the way we just argued in the last slide, okay, what happens, okay. So you have these NL layers, okay, and then at the receiver you will remove CP, you will basically take FFT, then you will estimate the channel, you will design the MIMO receiver. Let's come to this MIMO receiver, okay. We have reached that stage, okay, fine, okay. So we are considering the architecture which we discussed in the last slide. So what happens? There are NL different layers, right? Okay. So we spoke about this architecture, but we never went into detail of this. Okay. What is this? Zero forcing successive interference cancellation architecture. Okay. Right. So transmitter has transmitted 4 different layers. Okay. So what is this? What is this SIC architecture? Zero forcing we understand. Okay. Correct. So what are we saying here? So you have gotten this receive signal. Again, I have abstracted. I am not showing you the rest of the receiver chain. I just want to focus on that receiver MIMO receiver block. Okay. Right. So what happens here is that what will you do? Okay. So you look at, there are NL different layers. Okay. So what do? You look at first layer, NL is equal to 1. Okay. You demodulate it, you decode it. See, this is an abstraction. Okay. I am not showing you the complete chain. Abstraction means I am only showing you the relevant, the most important parts. Okay. To focus on certain things which are important in this case. Okay. Right. So what happens? So you have decoded this signal. Correct. Okay. You look at the first layer, because it was separately encoded. You can decode that. Right. Okay. All different 4 different layers, different processing was done. Okay. You have decoded it. Okay. Now what you can do is, what this SIC does is, okay, you have correctly, now you know what is your data, right? Once you have decoded your signal, you have validated it using CRC, you know that your decoded data is correct, right? Okay. Then what you do is, you re-encode the signal. Okay. What will happen from here is, you have look at this, where are we going back? You are looking at the receive signal. This is a complete receive signal. You subtract the contribution of that, because what have you done? You have decoded the signal. You know what your actual transmit signal is. Okay. It is like, if it is the receive signal is correct, okay, you know your actual data now. What you are doing here is, okay, you will regenerate this signal such that it is equivalent to the transmit signal. Okay, and remove its effect from the receive signal. Okay. So what are we doing? Transmit, when you have correctly decoded data, you basically remove its effect from the receive signal. Okay. What is happening? See, if you are transmitting 4 layers, what is happening? These 4 layers are interfering with each other, right? Because you are transmitting them on the same resource element. Okay. So they interfere. And we know that this receiver decouples these streams. Zero forcing receiver, what is it doing? H inverse, it decouples these streams and gives you 4 stream. Okay. Correct? Okay. Now what are we saying? This SIC receiver, what it does is, basically, it successively starts reducing the interference from the receive signal. Okay, because you have already detected this is correct. Okay, you know that after validating the CRC, you remove its effect. So in this receive signal, when you look at it, how many layers are being transmitted? If you look at this side of the receiver, this part of the receiver, for this part of the receiver, only 3 layers are being transmitted. Right? For this part of the receiver, let's say you have done for the second, you have removed the second stream, only 2 layers are being transmitted. For the last layer, how many layers are being transmitted? Only 1 layer. This layer does not even experience interference from rest of the streams. Okay, right? So now you are progressively reducing the interference which is experienced by each of the stream, right? And I can show you, and it's well known that this kind of receiver gives better performance than normal zero forcing receiver, wherein we don't do this SIC. Okay, right? So this kind of architecture, wherein each of this NL layer is undergoing different processing, you can do this, right? Okay, correct? Whereas whatever architecture we have discussed, can you do this? Up to NL is equal to 4 layers. Because you don't know unless and until you have basically validated the complete, there is only 1 layer, which there is only 1 coded block which is being transmitted. Right? How is that coding being done? You get only 1 modulated code block, right? For there is only 1 transfer block, you get only 1 modulated code word. How many code words you are getting here? 4. Right? Okay, you can validate each one of them, right, at the transfer block level, then you can remove its effect. Correct? Okay. In the current case, it cannot be done. right? Okay, so you cannot basically for up to 4 layers you cannot implement this SIC receiver. That's the limitation of that. Okay, fine. So you'll have to live with that limitation. What I'm claiming here is that this kind of architecture will give you better performance. The receiver will give you better performance because you can implement this kind of receiver, right? Okay. So have this idea in mind, okay, that if you implement a multi-code word transmission, which is not happening in standard till NL is equal to 4 layers, it is not happening, correct? What are you transmitting? You are transmitting only one modulated code word. Here there are 4 different code words, okay. Those 4 different code words, you can remove the interference from each of these code words successively at the receiver, okay. So what are we saying? So see, multi-code word transmission allows efficient implementation of zero forcing SIC receiver, okay. Then CRC is checked on decoded code word before a code word is cancelled. This cancellation happens, okay, from the overall received signal. We are looking at overall received signal and then removing the interference, okay, right. So, and this is, what will this allow is, only correctly received code words are cancelled, because you can validate the CRC. If the CRC passes, then only you subtract that code word, otherwise you don't. If you don't do that, you will, what will you do? You will subtract the wrongly decoded code word. So you have errors here, there will be error propagation in the other layers also, okay. So typically you don't do that. CRC helps in doing that, right? If this kind of architecture is given to you, you can do that, right? Okay. So this is one extreme, right? Okay. You see some flavor of it being there. If the rank is greater than 4, what happens? There are two code words, right? 2 transport blocks being sent. So it is being done in some form, right, provided the rank is greater than 4. But for less than 4, this is not being done, right? Okay. So this is, forget what is being done in the standard. This is one extreme wherein all NL different layers are coded and modulated separately. This is one architecture, correct? We understood what is the advantage of doing this, okay, right? What is the other architecture? You see this again when it rings a bell, okay. This is called single code word transmission. I am not talking about the standard, we are just seeing what is possible in theory, right? What is the single code word transmission? You get single transport block, coding and modulation, demultiplex, what is our layer mapper, okay, right, and then mapping I am calling as a precoder, okay, and then map it to anti-antenna. This mapping, don't confuse it with our standard mapping, this is the precoder part, okay. Demultiplex, precode it and send it over different antennas, okay. What is this? This is, you are getting a single code word, single transfer block. Now if it is NL is equal to 8, you can do this also, okay. NL is equal to 4, anyway we are doing it. What is happening? This is, isn't this same as what we are doing for NL is equal to 4, right? What is this? You get single transfer block, demultiplex and precode. That's what we are doing, okay. You can do it for 5, 6, 7, 8 also. Why are we not doing it? Why are we transmitting 2 different, why is MAC sending 2 different transfer blocks? That's what we want to argue, correct, okay. This is another architecture, okay. So MAC gives a single transfer block to which physical layer adds CRC and performs coding and modulation, right, okay. This is another architecture. So what happens? So for NL rank channel, transfer block size here is NL times multi-code transmission, because in multi-code transmission you are transmitting NL different, MAC is sending NL code words or NL transfer blocks. Here it is sending only one transfer block, so the size of transfer block in this case will be NL times the last case, okay. Coded and modulated symbols are then demultiplex for transmission over multiple antennas. This is whatever I have explained in figure, I am writing it over here, okay, right. So the optimal receiver for single scheme like this, okay, is a very high complexity receiver, maximum likelihood receiver, okay. I have not taught you this, but it has a very high complexity, okay. This architecture cannot use zero forcing receiver. Why? We just argued, right, that zero forcing receiver, there is only one code word. What will you subtract, right? Okay, you cannot, you will, if there is only one code word, right, you will have to decode all of that. There is no other code word left. Whose effect you are going to remove? Okay, correct? So that's why you cannot do successive interference cancellation for this kind of system, which is single code word transmission. Okay, right? So what am I saying here? That if you want to get the best performance for this kind of system, I have taught you, like, whatever receiver design zero forcing, they are suboptimal, they give you inferior performance. Okay, this maximum likelihood receiver gives you the best performance, but it has a very high complexity. Okay. Now, so this, for this kind of architecture, if you want to get the best performance, you will have to implement this maximum likelihood receiver. Okay, not whatever we discussed. Okay. So the summary of this is, okay, that there are two extremes, okay, wherein either you do this, wherein MAC layer gives you only one transport block, you multiplex them into NL layers. NL can be 4, 5, 6, 7, 8, doesn't matter. Okay, right? Or there is this other architecture which I showed you in the last slide, wherein each, if depending on the number of layers, MAC gives you NL transfer blocks. Here it gives only one transfer block. These are two different extremes, right? Okay. Now, what is happening here? So this is the history. This is the discussion which went on. Okay. This will answer most of the questions what we have in mind. Why different kind of architecture? Why the architecture which is there in the standard is implemented the way it is? Okay. So when these architectures were being debated, okay, they were debated with 4G also. Similar kind of architecture is there in 4G also. Okay. So look at it. These decisions I am talking, we got to know about from 4G days. So this is applicable here for 5G also. Okay, right? So both these architectures were considered, single code word and multi code word MIMO architectures. Okay, correct? And then what happens? Performance and complexity trade-off of both these architectures were considered. Okay, one should give, what is the advantage of one architecture over other? Okay, so single code word versus multi code word, what are the advantages and limitations? That's how, now it is, we understand few things. What happens in multi code word transmission? You can implement the zero forcing SIC receiver, which I am claiming has a much lower complexity than the maximum likelihood receiver. Okay, I have not taught you, but if you are interested, you can check that. Okay, how is maximum likelihood receiver implemented for a MIMO system? We have spoken about it for a CISO system. Okay, so this multi code word transmission helps in implementation of low complexity zero forcing architecture. Okay, right? Single code word has high complexity, requires a high complexity ML receiver, okay, if you want to get the best performance. So look at the receiver, one allows implementation of low complexity architecture, other allows, you will have to implement a high complexity ML receiver. But this should also have some limitation, that's what I'm, okay. Now single code word scheme requires lesser signaling overhead. What happens? Let's look at this, okay. Correct, this is slightly old in this context, but look at this. Okay, if it is a single code word architecture, okay, or it is a multi code word architecture, right? What will happen? Because if it is a single code word, that code word will be transmitted with the single MCS. Right? How are you doing if it is a single code word transmission? Each one of, there is only one code word, one transfer block, and that transfer block has to be encoded using a particular MCS. Right? Okay, correct? And then UE, who feeds the MCS? UE feeds the MCS. Right? So if it is a single code word transmission, UE will have to feed back only single MCS. Right? Correct? Even though the single code word requires high complexity ML receiver, but the signaling overhead, okay, which is basically single MCS, right, wherein UE feeds back MCS only for single transfer block, right, or the single code word. Okay, that's so. this single code word transmission, even though it requires high complexity receiver, it requires a lesser signaling overhead. When compared with multi-code word scheme, it requires larger signaling overhead. As what does UE need to feed back? It needs to feed back ACK or NACK for each transport block, right? Okay, this is okay. So hybrid ARQ operation is performed on each transfer block because there are two different transfer blocks. Okay, more than this, transfer block size and MCS separately for each transfer block. Now there are like, if you do this multi-code word transmission, how many code words you are transmitting? You are transmitting multiple code words. For each of this code word, right, UE will have to transmit MCS. Okay, that is increasing the overhead, right? Okay. Now, so after carefully evaluating the receiver complexity and signaling overhead, what was done? That's where all this comes into picture. What's happening? A trade-off was arrived, okay, wherein it was said, okay, it was decided that it is whatever transmission we have, you look at it, it is a hybrid between single code word and multi-code word schemes. How it is hybrid? Because if the rank is up to 4, you transmit only one code word. If the rank is greater than 4, you transmit if the rank is greater than 4, you transmit 2 different code words. Okay, right? So this is a summary, but at the end of it, what are we saying? Okay, right? So if it is a multi-code word transmission, okay, UE will have to, for example, will have to feed MCS for each of this code word. That requires a high signaling overhead. Okay, right? Even though multi-code word transmission will allow you to implement a simpler receiver, which is zero forcing SIC receiver. Correct? But the signaling overhead is high. Okay, when compared with single code word transmission, okay, UE will have to feed back MCS only for one code word. So signaling overhead is low, but the receiver complexity is high, right? Okay. So what is this? This is sort of trade-off whatever architecture we see, right? So if the rank is up to 4, you transmit only one code word. The rank is greater than 4, basically transmit 2 code words and do zero forcing SIC, implement SIC across these 2 different transfer blocks, right? Okay. Then what happens if the rank is greater than 4? Anyway, you know that UE has a good channel, right? So it will support a higher data rate. Then even though the signaling overhead is high, you don't mind, right? Because UE is observing a good channel. So even if it will anyway going to get a high data rate, even if the signaling overhead is high, so you will have to support that, right? Okay. Because if the rank is up to 8, it essentially means a very good channel, right? The rank is up to 4, and compared with it, it is a degraded channel. Okay, even though in isolation that itself is good, right? Okay, fine. So what are we saying here? Whatever architecture you see, it is basically a trade-off between the receiver complexity and the signaling overhead. Okay, right? So it is neither single code word nor multi-code word. It is a hybrid. Okay, right? And each of this architecture has its own advantages. And this kind of hybrid architecture tries to capture both of them. Okay, right? So I'll stop here. This brings us to end of a certain part of MIMO discussion. Okay, in the next class I will start something new on MIMO. Okay, I'll stop here. Thank you.